This is 733 in U Waterloo's numbering system. And I looked online, and it's supposed to be called, I think, quantum many-body physics. Hey, guys. But I think it's just listed as a reading course for you guys that are enrolling here at Waterloo. So I don't know what the story is with that. I think the story is this is only the second time this course has been offered at Waterloo. And so the registrar hasn't quite got the calendar updated yet. So I'm not sure what the equivalent is at Mac. But let me just go through the course outline real quick. So before I start, so what I'm going to do with all the course material, including all the notes that I put on the board, is I'm going to upload them to a Dropbox folder. And so the first thing you guys should do is send me an email. And I'll make a class list from this email. And I'll also give you, I'll also share the Dropbox folder. So you'll have the link, and you can get all the lectures and assignments and the course outline that I'm going to tell you about right now. So that's RGMELKO at UWaterloo. Okay, and I'll basically have you guys we'll either get your assignments through regular exchange with Mac, some sort of I'll have somebody bring them over, hard copies, or you can also even just email me them if you happen to LaTeX them or so on. So let me just talk about the course outline real quickly. So I have, if you haven't seen this, it was in emails that were sent around. I'll upload it to a Dropbox folder today. But basically, it's pretty simple. We have lectures Tuesday, Thursday. At this time, 10 to 11:30. And then the grade breakdown will be just assignments and a computational project. So 80% of your mark will be assignments. I think last time I gave 5 of these assignments, and they're like graduate level assignments, right? They'll take you a couple weeks to basically complete. And then about halfway through the course, or maybe a third of the way through, I'll give you a computational project. Which is the remaining 20% of your grade. And that'll be some sort of numerical exact diagonalization type program that you'll be running to sort of complement the stuff that we'll be doing in lecture. Okay, so I call it a project because the assignments will be analytical work on quantum many-body physics. We're doing path integrals, we're doing types of field theory, we're doing exact calculations analytically. But the computational project's meant to complement that with something we'll be doing, on the computer, something numerical. And so that's something that basically you'll have to be a bit resourceful. I don't know how to make this board stick. And come up with some of the reading and the background material on your own. In terms of prereqs, so at UW, it's 701 and 704. That's quantum mechanics and stat mech, the first stat mech. And so whatever it is for you guys at Mac, basically you need introductory quantum mechanics and you need to know what like a partition function is. And if you don't know what that is, come talk to me. And so if you don't have these equivalent prereqs, I can just sign off on them. Like if you're taking 704 the same semester, for example, or something like that, I can just sign off on that. So who's a theorist? Who's an experimentalist? So we're split about a 50-50 here. Who's doing condensed matter? And quantum information? Quantum chemistry? No chemists? Okay, good. Last time I had a whole bunch of chemists. That screwed the vibe up, man. Okay, so this is good. So, so we'll be covering topics in both condensed matter and quantum information. But since I'm a condensed matter person, this will be tilted a bit more towards the condensed matter perspective. So we're going to start off today with transverse field Ising models. And the transverse field Ising model is one of the simplest ways to demonstrate this classical to quantum correspondence, or quantum to classical correspondence. And you're already familiar with, quantum classical correspondences in some sense. I mean, the way that you're used to dealing with quantum mechanics maybe is from an operator perspective. You have non-commuting operators that give you sort of all the fundamental structure of quantum mechanics. And what we're developing in this class is more of a path integral approach. So you might have heard of Feynman path integrals. It's some idea that like in the two-slit experiment, if you have an electron moving through a slit, and there's all these different paths that the electron can take, right? And there's, quantum mechanics can be rewritten as some sort of integration over all possible paths, right? And what happens in this type of path integral approach to quantum mechanics is sort of the fundamental importance of the operators gets swapped out for something in sort of a higher dimensional space. That higher dimension turns out to be related to this integration. So it's just another way of sort of taking a quantum mechanical system and handling it in a classical manner. Okay, and so the transverse field Ising model is a way of sort of really making that concrete. And so we'll start out very concrete with a specific Hamiltonian, which we'll introduce today, and then we'll move on to slightly more abstract things. So then we'll talk about basically just general many particle path integrals. And we'll talk about bosons, fermions, and also spin path integrals, so spin coherent states. And we'll see that the fundamental thing that you might have thought was quantum, when you're dealing with sort of single particle operators and so on, will look a little different when we look at the many particle path integral. So something called the Berry's phase becomes quite important. All the quantum mechanics that you're used to thinking about as being quantum get transformed in different ways, so that a lot of what's quantum in a path integral turns out to be a geometrical phase called the Berry's phase. And that'll come out in the in the coherent states that we'll derive. We'll talk a lot about quantum critical points. And we'll do, this quantum critical points and quantum phase transitions is really the topic of 705, Physics 705. So this is related. 705 is the second stat mech in UW. So 704 is, I don't remember, it's like statistical physics 1, and this is statistical physics 2. But really what 705 is the renormalization group. And the renormalization group is that thing that, is that theory of essentially phase transitions that gives you universality. And the kind of awkward thing with alternating 705, which I teach, in odd years, and 733, which we're taking right now, is that we're not going to encounter universality in this class. Okay, so universality is the phenomenon that connects the low energy effective theories that we might be deriving in sort of a more abstract path integral sense with, say, a phase transition in something like lithium homium fluoride that might be an experimental system realizing a transverse field Ising model. Or it might connect, phase transitions in I don't know, polymer systems or liquid crystals and magnets and liquid gas transitions and stuff like that. So even though the sort of underlying path integrals and the underlying field theories that we're going to study are related to the quantum critical points in some very deep way, you're not going to get the full stat mech treatment of universality unless you take 705, which I recommend taking. I mean, that's probably the coolest course that's offered around here. We're going to talk about also about just kind of 5-4 theories. Okay, so quantum critical points, many particle path integrals. At the end of the class, we're going to be more abstract. So we're starting out concrete, and we're sort of working up to, I don't know, like, I'll just call them 5-4 theories. So these are just quantum field theories, you know. Which you could take in another course. You could take a high energy field theory course, and you'll go right into 5-4 theories without being motivated through sort of this condensed matter perspective. So one of the amazing things of, one of the amazing things with field theories is the same field theory will describe a whole bunch of phenomena in condensed matter as well as in high energy systems. So there's and really this sort of universality and quantum criticality plays a big role in this. But just the structure of the theories is very similar. So that's something that we'll definitely see a little bit of in this class. We're going to talk about Ising Gage theories too. So Ising Gage theories are topological in nature. And I'll explain what that means. But these are very important for sort of experimental efforts to develop topological quantum computing. So this is also a condensed matter topic in a sense, but it's also related to quantum computing. And I think it's sort of a topical, it's a topic of current interest because, as you may or may not know, there's several efforts around the world to build topologically stable quantum bits, essentially. And these Ising Gage theories are sort of the most toy or the most basic model that we can relate to this type of effort. And finally, we'll be talking about some numerical methods. In diagonalization techniques. Which is mostly feeding into your computational project. Okay, so numerical methods will be sort of applied more to Hamiltonians, to actual lattice models. Whereas stuff like path integrals and 5-4 theories, quantum field theories, those actually occur in the continuum. Okay, so there's this sort of duality between lattice models and continuum field theories that we'll explore quite a bit in this class. I have a whole bunch of recommended texts for these topics, but I don't have one textbook for this class. So I even hesitate to give you a list of recommended texts, because you're just going to have to find a text that you like, or a series of texts that you like. And when I'm discussing different topics, I'll give you guys sort of references that you can look at, in real time. But some of the books, like maybe Xiaogan Wen's books, may be interesting to give you another perspective on what I'm talking about. Eduardo Fradkin's second edition of his quantum field theory book, I forget what it's called. Anyway, Fradkin's book is another good one. Altland and Simons is what they use in Toronto for this class. So I think when Jan-Beck Kim teaches this, they use Altland and Simons. So there's, the list is on the course outline, but like I say, there's no one textbook I think that'll cover everything I talk about. That's all I have for organizational stuff. We're just going to head right into transverse field Ising model. So any questions about what's going on here? Has anyone encountered any of these topics before in a class? What have you taken at Mac before that's related to this? You've all taken introductory stat Mac, right? Anyone take the second stat Mac, like an advanced stat Mac, like renormalization group type stuff? Auditing is probably enough to get the gist of what's going on with sort of universality and this type of thing. Fixed points, you know. What about you guys here? Anyone know what a fixed point is? Before, it's been a while. Cool. All right. So we'll sort of avoid that language, I think. But like I say, I encourage all of you to take 705 or the equivalent because it really ties everything together. This idea that you have critical points that are sort of fixed points of a theory, you know, everything flows to them in some RG sense. And then it just takes all of this abstractedness or whatever it is that we're going to be dealing with and really relate it to all these other topics. So that's my plug for 705. Okay, so let's just start in. We'll define a many-body Hamiltonian, so a simple spin Hamiltonian for the transverse field Ising model. This will take us a couple lectures, and we'll look at the properties of this model, okay, like its phase diagram and its thermodynamic properties. And this is just to get us sort of warmed up for, I guess, the type of problem we're looking at in this class. And slowly we'll derive the sort of quantum to classical correspondence, the path integral representation for the transverse field Ising model. And so one thing about these path integrals that we're deriving that you'll notice, you should think about as we do it, is they're always in one higher dimension in space, or space-time, or imaginary time, you might call that other dimension. So if we have a d-dimensional Ising model, say a 2- or 3-dimensional transverse field Ising model, the path integral that we'll be deriving is actually one dimension higher. And that's a real fundamental feature of this type of quantum to classical correspondence. Okay? So let's see how that plays out. So just sort of a review of some topics in quantum many-body physics, which may or may not be many-body. So we're interested in Hilbert spaces. And operations on those Hilbert spaces, which gives us the idea of an operator. Hilbert spaces and operations thereon. I don't know if that's a word. It is now. And the whole problem the whole challenge, I guess, of quantum many-body physics is the size of this Hilbert space, of course. So, for example, if we have n spin 1/2 particles, and we're really talking about the spin is the degree of freedom that we're interested in. So if I have a system of electrons, or say a metal or something like that, where the electrons live in the metal, there's all sorts of different quantum species and quantum particles in that metal, right? There's the ions in the crystal. There's maybe many electrons that are trapped in valence bands, and there's some in conduction bands maybe. And what we're really doing when we say this is we're only isolating sort of one quantum number of one set of those electrons typically. So we've already separated out a whole bunch of length scales and energy scales when we talk about spin 1/2 particles. What we're really talking about is just the spin, if you want, degrees of freedom of a certain subset of electrons in a material. So for n spin 1/2 particles, you all know what spin 1/2 means. If I take the expectation value of the SZ operator, I get plus or minus 1/2, right? So those two different outcomes give us a Hilbert space that's of size 2 to the n. And that's where all the problems lie, of course. So if you're interested in even representing the Hilbert space, even writing down the Hilbert space, that number is exponentially big. So say if n is something like 40, so 2 to the 40 is, I wrote it down, 10 to the 12. No, 10 to the 12. 10 to the 12 is the number. It's the number of bits that you would need to represent the Hilbert space or something like that. And if you just imagine putting this in memory, I forget what 10 to the 12 is. Whatever. You know, it's like, it's the biggest computer essentially that we have. So that's just to represent the Hilbert space of n to the 40, of n equals 40, which is a very small system size. And if you get to something like a 16 by 16 lattice, so if I had 256 spins, if I was representing 256 spins, say on a lattice or something like that, this is 10 to the 80. So the size of the Hilbert space is greater than the number of particles in the known universe. I forget if that accounts for dark matter. But it's like 10 to the 70 or 10 to the 80 is the number of particles in the universe. So it's greater than the number of particles. So there's something fundamentally complex about the Hilbert space, right? There's a complexity that exists that can't be, you know, somehow captured by classical ways of thinking. And this whole idea of the inability to even store the Hilbert space, to store all the different states, right, for say a 16 by 16 lattice, really motivates us to think about these problems in a different way. So we don't give up. You know, we don't just say, okay, well, there's no point in even trying to solve any of these problems. We basically lay down a strategy for what we're interested in looking at, and we find ways of attacking problems even with these huge exponential Hilbert spaces. So in this class, we're interested in sort of thermodynamic properties. And those stem essentially from solutions to the time independent Schrodinger equation, right, which is h operating on some wave function, giving back the energy eigenvalues of that wave function. Energy eigenvalues, you know, that eigenequation. So this, you know, and if this is the ground state, then we'll get ground state properties of the many-body system. And that's typically in condensed matter systems. That's what we're interested in. Ground state properties means things like, you know, broken symmetries or something like that. But also we can imagine that this is an excited state, and maybe we want to know something about the excitations. Okay, so the elementary excitations. And in particular, you might ask, what's the gap between the ground state and different elementary excitations? That's a very fundamental property in condensed matter. If you take condensed matter as a class, that's basically the problem that you're solving. Is what's the ground state? You know, what's the elementary excitations out of that ground state, right? It's like, say, like phonons or something like that might be an example, right? Phonons are a collective, you know, a collective quantum many-body phenomena where lattice vibrations are quantized. I know there's a dispersion and so on, right? And if you're at a certain momentum, that dispersion might be gapless. You know, the difference between the ground state energy and the first excited state would be 0. And whether or not things are gapped or gapless is very fundamental. Quantum critical points, so any sort of second order phase transition that occurs in a quantum system is typically gapless, right? There's many excitations that live at low energies. Goldstone modes. So if you have a symmetry breaking, and if you have a continuous symmetry breaking, then you'll get Goldstone bosons, which are another gapless phenomenon.
Is it always solvable? Like, do you always know there's a gap or there's no gap?
No, it's not. I think even in terms of a complexity issue, it's not always solvable, right? But this is sort of the physical thing that you're interested in. And this is one of the motivations that we have in condensed matter, is to sort of explore properties of systems and determine whether or not we have a gap. It's a little it's kind of a simplistic way of saying it, but I think that's a good sort of overarching philosophy here. So in general, no, it's not exactly known how to solve for these gaps, and that's one of the things we're going to deal with in this class. Another motivation, another interest is also topological properties, which aren't exactly related to this sort of ground state elementary excitation issue. So maybe topological invariance is another way of saying it. So you could have a ground state that has all sorts of properties. Maybe it has symmetry breaking or something like that. You know, so if you guys are doing neutron scattering, right, what you're really looking for is say the structure factor, which gives you an idea of the broken symmetries in the ground state. You might also want to know the dispersion, which will give you an idea of the gap. And the form of the dispersion gives you an idea of the elementary excitations. Are they phonons? Are they, you know, electron quasi-particles with a different mass or something like that? Topological invariants are something a little different. These tell you whether or not you have topological properties in your system that have certain, you know, invariance means that you can modify your system in some way and still retain a number, say. So a lattice gauge theory, so Z2 lattice gauge theory in 2 dimensions, has a type of topological order, which is a topological property that's invariant under local transformations. And that's what gives you the idea of a topological qubit, for example. You also have topological insulators that have a topological invariant as you pass from the bulk of the insulator and you pass through the surface to the trivial, you know, vacuum insulator on the outside. There's a topological invariant that you have to deal with. And so we'll talk a bit about topological structures of theories in this class, but it's something to just keep in mind that's sort of outside of this picture of ground state and elementary excitations. So what does this have to do with this, the solutions to the time-independent Schrodinger equation? Well, as you know, basically the ground state, you know, the expectation values of different operators in the ground state will give you, say, you know, the idea of the symmetry breaking and so on for excitations. But then you have to essentially know what the solution to that problem is, right? You have to know the eigenvalue problem. So you can also transform this into asking about finite temperature properties of a system. And that's like taking your density matrix which is just the outer product of your wave function so compare this to the thermalized density matrix, which I can write as a sum over e to the minus, okay, so I'll say ei, yeah. So I've just chosen some basis, sum over all elements of that basis, and I've defined beta as an inverse temperature. And the Boltzmann constant is some way of relating temperatures to an energy scale, essentially. And we'll just set it to 1 all the time. So in order to do this, in order to basically, you know, extract a thermal density matrix, if you want to call this object that, you essentially have to know, you know, what the, you know, you have to know how to solve the eigenvalue problem. Same for time evolution, right? So this is all, I'm imagining sort of static properties of a system. If I want to time evolve a system, it's the same thing. right? So for time evolution, you're taking your wave function and you're applying the time evolution operator, which I just called t there, starting at t naught. So I take a wave function at some time t naught, and then I want to time evolve it to some later time through this operator, and I get the wave function at some time t. I'll use this notation for the time evolution operator. We'll start calling this a propagator later on, and we're going to propagate our sort of d-dimensional quantum systems into this d plus one dimensional imaginary space-time using a propagator like this. And you'll see why I call it imaginary time when I do that. But in this case, I'm just talking about motivations. The time evolution operator, of course, requires knowledge of the Hamiltonian, which essentially is, again, solving the time-independent Schrodinger equation there. And I could say the same for other unitary operators. Oops, OTH. So we might also be interested in the effect of other unitaries on a quantum many-body system. And it'll essentially require solutions to the time-independent Schrodinger equation. So all of these things imply that the full solution essentially amounts to diagonalizing the Hamiltonian. So if you had a discrete Hilbert space, which I like to think of lattice systems get by a lot of problems with the continuum. Okay, so imagine you have a lattice of many qubits, and you wanted to calculate any of these sort of properties of interest. The most straightforward thing you can imagine doing is to diagonalize the Hamiltonian. And we will diagonalize Hamiltonians in this class numerically. It'll be part of your computational project. And you'll soon see that full diagonalization of Hamiltonians essentially gets you almost nowhere in the field of quantum many-body physics. Because even for simple spin 1/2 systems, and by simple, I'd have to define the Hamiltonian, which I haven't really done. But for simple Hamiltonians with high symmetries, say, the maximum number of spins that you can diagonalize might be something like maybe 16 if you're doing full diagonalization, full spectrum diagonalization, say, to get thermodynamic properties, where you need all of the spectrum to do this sum. And if you're only interested in the ground state, you might be able to sort of pare that down a bit. So maybe you can get, say, 20s, maybe low 30s. And that's for this, that's for the simplest, the local Hilbert space for spin 1/2 is the lowest possible dimension for your Hilbert space, essentially. So even these very simple spin systems are almost intractable with diagonalization. Now, I should say, if you want to know the properties of 16 spins, that's fine. But when I talk about many-body systems, and especially if we're talking about condensed matter applications, we're typically talking about the thermodynamic limit. Thermodynamic limit. So you have to ask this question. If I can diagonalize 16 spins, is that enough to determine properties of the thermodynamic limit? And typically the answer is no, although in some cases you might be able to get some rough properties of the thermodynamic limit. So this is sort of a separate question. Well, I'll just mention one thing we're going to do in the computational project, and that has to do with Lanczos diagonalization. So if I'm talking about full diagonalization, 16, maybe 20, if you like, if you block diagonal in the Hamiltonian or something like that, we can also do approximate. Iterative. So I'm basically just telling you this, not because, because we'll do it, but also less as a sort of fundamental, I guess, concept. Iterative diagonalizations are what's used in practice. So they go under the name Lanczos, or sometimes Davidson techniques. So people doing quantum chemistry, typically, they're solving for the energy, rotational and vibrational modes of molecules and stuff like that. A lot of their toolbox is based on iterative diagonalizations such as Lanczos, very clever iterative diagonalizations. And the idea there is that sometimes these are called projector methods or power methods, is that you take the Hamiltonian and you apply a very large power of the Hamiltonian to a trial state. I've just called it alpha. And if that state is written in terms of a decomposition into the, say, energy eigenbasis with coefficient C, then I can write this high power of the Hamiltonian. So I want to pull out C naught and the ground state energy, the magnitude of it to some power. Right, then I can write this basically as just the energy, the ground state energy. So I'm working in the energy eigenbasis, plus, and then something like this. So E1 over E naught to the M1 plus other terms. So these power methods, so what I've done is I've arranged the Hamiltonian such that the ground state energy is the largest in magnitude. And what happens is you project out to increasing accuracy with larger and larger powers, the ground state, whereas the first excited state contribution goes to 0 because this ratio, this ratio goes to 0 as m goes to infinity. It's very simple in some sense, but this is the sort of technological basis for a lot of numerical techniques. And with these types of techniques, you can get ground state solutions to the time-independent Schrodinger equation. So ground state energy eigenvalues and eigenvectors for maybe, spin systems, something around 40. That's with all sorts of symmetries on very simple Hamiltonians and spin 1/2. So I'm just giving you an idea of the state of the art, sort of. But even the state of the art maybe isn't all that impressive in terms of many-body diagonalization. But if you read the literature, you'll see lots and lots of studies that use these types of techniques. And in condensed matter, you'll see a lot of people using diagonalization on this size of system or smaller to try, and they're using that data to try to infer something about the thermodynamic limit. There's other methods, just to be sort of complete. And they're not all based on diagonalizations or iterative diagonalizations. We also have series expansions. So say high temperature. Which last time I taught, we actually did some series expansion in the computational project. I have to think about whether or not I want to do that again. These are sort of biased techniques. So if I take, we'll do some examples where I essentially take maybe a Hamiltonian and I write it in terms of 1 over beta or something like that. I can get a high temperature series expansion that's sort of a perturbation theory. Okay. The problem with a perturbation theory like that is it's always biased. It'll work well if you want to calculate high temperature properties, but if you really want to infer something about the ground state, it might not work. But still, series expansions enjoy quite a lot of success in sort of the many-body community. My favorite is Monte Carlo, or quantum Monte Carlo. So Monte Carlo are stochastic-based methods. That means you probably know what a sort of simple Monte Carlo looks like. You might have Ising spins or Ising variables, and you might, randomly try to flip spins in the system and calculate a weight or a probability for that state to occur. And then, you update accordingly and calculate thermodynamic estimators. And I mean, these, depending on what your Hamiltonian looks like, we're talking about 10 to the 6 or 10 to the 8 spins are typically solved. Statistical equilibrium, finite temperature properties on this size of system. So that one drawback is Monte Carlo essentially gives you equilibrium stat mech. So there's going to be no time evolution. There's going to be no dynamical structure factors if you're calculating neutron scattering properties, for example. You can't get S of Q omega from a Monte Carlo. And in terms of the quantumness, there's sort of fundamental problems with I guess representing quantum systems as a probability or a probabilistic process, and that's related to the fermionic sign problem. And that's hard to explain, but this is a sort of fundamental restriction on which Hamiltonians, I guess, you can solve stochastically with Monte Carlo techniques. So it's a fairly severe restriction. So for example, superconductivity, Coop rates, high TC, the sort of toy Hamiltonians are known for the Coop rates. There these so-called Hubbard models. The Hubbard models are two-dimensional models of electrons in second quantized form hopping on a lattice. And these electrons have interactions, Coulomb interactions, say, or something like that. The underlying properties, like all of this stuff that's motivating us, isn't exactly known for the Hubbard model. The Hilbert space is bigger than spins. So instead of just having 2 to the n, you might have 4 to the n or something like that, depending on how many orbitals and so on. And all of a sudden, diagonalization becomes really useless. You're dealing with maybe a maximum of like 10 particles in terms of these electronic degrees of freedom. So you might say, well, I need something better than diagonalization. There has been a lot of series expansion work, which is more or less successful in some sense. But Monte Carlo, which you could really nail the thermodynamic properties of the Hubbard model with, suffers from a sort of fundamental restriction in the sign problem, such that you can't even determine the ground state energy or anything. And this sign problem is actually very fundamentally interesting. It's maybe some people believe it's a computational complexity issue. Are there certain quantum Hamiltonians that just can't be solved on a classical computer? And since Monte Carlo is the best method for solving equilibrium stat mech properties, the idea that certain fermionic systems and frustrated spin systems fail with Monte Carlo gives people the idea that there's maybe something fundamentally complex about, say, fermions in this sense. And this is motivated development of other quantum numerical methods, such as the DMRG. Who's heard of the DMRG? Nobody? Okay, then forget it. It's the density matrix renormalization group, which is related to tensor network methods. Tensor networks are another way of representing quantum systems, biased in some sense, not towards high temperature or something like that, but biased towards low entanglement properties. So it's a very fundamental quantum mechanical way of representing systems. And these things have sort of garnished a lot of success in exploring quantum many-body systems. And one reason I mention these is there's experts here at Perimeter on DMRG and tensor networks. So for example, Guy Vidal has developed a lot of technology and theory in terms of tensor networks. And so if this is some, if you ever pursue the sort of state-of-the-art in terms of computational methods, just keep these words in mind, I guess. So these are the things that would come to my mind if I wanted to solve a quantum many-body system. And we're not really going to pursue these because we're going to take an alternative approach. But before I talk about that, there still is this elephant in the room, I guess, where you could say, well, why am I worried about representing the Hilbert space on a classical computer? Won't quantum computers solve all of these problems for me? And that's a good question. There's different ways of imagining quantum computing contributing to these problems. So there's different types of quantum computers. And of course, we're all working on quantum computers in some way or another. So we should think about these different types of quantum computing. So for example, for the problems we're talking about, we can imagine just essentially emulating, the quantum Hamiltonians that we're interested in, like the Hubbard model, using a real analog quantum computer. And that's actually maybe one of the most immediately applicable approaches to quantum computing. So just my simple review of quantum computing and how and why we care about it. Let me start from the easiest to the hardest. Quantum annealing maybe is the easiest to implement. Ooh, I don't know how to spell that. 2 N's or 2 L's? Let's do 2 of both. That's definitely wrong. So quantum annealing is like, this is what D-Wave does, or claims to do. This is a type of quantum computer where you're just solving some sort of very complex optimization problem. It's like you have a rough free energy landscape or rough energy landscape of some classical Hamiltonian, and you want to find the ground state or the absolute minimum of that free energy. And the quantum tunneling process helps you somehow. That's very simple to implement. I mean, relatively speaking, right? If you read any of the literature on D-Wave, or more recently Google's hired John Martinez from UC Santa Barbara to basically build another D-Wave machine, which is just a quantum annealer. And the reason I think these companies are pursuing, this technology is it has something to do with, optimization problems have something to do with machine learning, and there's some connection there that I think investors are willing to sort of fund. The thing I'm talking about, okay, so this is simplest. There's something in between the simplest sort of quantum computer and sort of the universal gate. which is the most powerful, general quantum computer. Which essentially at IQC, this is what people are working on in some sense, gate models for quantum computing. And when we typically think about quantum computing, this is what we're thinking about. It's the analog, which is the wrong word, of our universal classical computers, right? Or our general purpose classical computers, where you have this gate, these gates operating on registers and so on. This is very difficult to implement. It's not even clear that it will ever happen. And the amount of qubits that you need in order to solve like Shor's algorithm or something can be very large. Okay, so this is easy to hard to implement. So this is very general purpose, and this is a very specific optimization type of quantum computer. And in between those, you might imagine I'll call it an analog quantum computer. Or maybe an analog quantum simulator. And what an analog quantum simulator would be a quantum mechanical system that would, say, implement something like the transverse field Ising model directly. So instead of trying to do digital computation and solve thermodynamic properties, say, of the transverse field Ising model, what you can imagine doing is implementing the transverse field Ising model and then measuring on that analog simulators things like the energies and so on. Okay, and this type of quantum computer is probably one of the most useful scientifically for us at this stage. And by this stage, I mean this stage of sort of technological development, because if you just look at the size of the Hilbert spaces I'm talking about, if you could essentially get an analog quantum simulator that had something like n greater than 40 qubits, then you'd already be in business and you'd already be solving problems that can't be solved exactly using any of these sort of numerical techniques that I'm talking about. Okay? So the quantum annealing type of machines like D-Wave, these already have thousands of qubits, amassed in arrays. But those qubits are maybe noisy, high temperature things that are difficult to characterize and control. So this is sort of it's a different type of quantumness we're talking about. Adiabatic quantum evolution or quantum adiabatic algorithms, they're not even known to, theoretically necessarily give us any sort of quantum speed up. So these are very specialized machines. These things here require real qubits. We require exquisite control of all sort of quantum processes that are going on at the qubit level. But they will give us useful results at a much smaller number of qubits than sort of universal quantum computing, will for, like, how many qubits do you need for non-trivial Shor's algorithm? It's thousands or something like that, right? So we're talking about, n greater than thousands of qubits here. So when people ask you whether or not quantum computing will solve the problems that we're dealing with in this class, I'd say the best hope that we have is something like an analog quantum simulator, which could be like a cold atom system, an NMR system, even a superconducting quantum circuit. So in some sense, Matteo Mariantoni is interested in this question at IQC. He wants to use superconducting quantum circuits to build qubit arrays to study many-body physics, and specifically topological many-body physics. So in that sense, what he would be building on a few qubit system could be like a quantum simulator or quantum emulator for the types of problems that we're going to discuss in this class. Okay, what am I rambling about now? All right. So instead of, we're not going to do any of these techniques in this class. What we're going to do in this class is sort of traditional, I guess, analytical techniques. And traditional analytical techniques for the many-body problem involve all of these things that are in the outline in some sense. So deriving effective models. Effective models means you're stripping away a bunch of the degrees of freedom that you don't really care about, like all these electrons in the valence band, or something like that, right? All the ions in the metal that you don't care about. Low energy effective theories, okay, of these models this is where your field theories come in. So I'm going to introduce a model right away, the transverse field Ising model, which is in and itself just an effective model. It's stripped away a lot of things down to just the degrees of freedom associated with the quantum spins, right? And then you apply techniques that separate out energy scales or length scales such that you can only look at the low energy properties of that model. Okay? So you have to sort of wrap your head around the fact that there's separations of energy scales going on. Even in this approach where we're imagining solving, a 20 spin lattice model, we've already, defined an effective model because we've maybe cooled the thing down to low temperatures where only the spin degrees of freedom matter. So a lot of what we're going to talk about in this class is developing low energy effective theories for these models. And we can do that because of separation of energy and length scales. Okay? And this is where our field theories and our concepts of universality and so on come out. And universality is also another powerful analytical way of understanding things, or a powerful conceptual way of understanding things. But essentially, universality is the entire topic of 705. Okay, so I'll mention it when it's important for our context, but we really won't deal with it until we start looking at 705 and the idea of the renormalization group. And part of the things I'm trying to do with this class is also introduce these techniques to those of you that may never use them. Okay, so it's quite probable that if you're a theorist and you're working on solving quantum many-body systems, you might be working on some sort of numerical technique or some sort of conceptual algorithmic techniques like this. And if you're an experimentalist, very likely you'll never actually do field theory calculations, but you're going to have to talk to field theorists, And I think part of the motivation for the way I'm teaching this class is to give you a basic fluency in what field theory and what analytical theorists are talking about when they talk about the many-body problem. Okay, so it might seem a little slow the way we're starting out, but trust me, by the end it's going to be very abstract. And so what we're doing here is we're just building up a foundation for all of this, low energy effective quantum field theories that we'll basically use throughout. So let's keep that in mind and start with the transverse field Ising model. It's a nice way of grounding the discussion because it's the simplest example of an interesting quantum many-body system. It's like the hydrogen atom for quantum many-body physics. It's been studied to death, but you learn about how to perform calculations. You learn about the conceptual framework of the path integrals and so on from the transverse field Ising model. So it has interesting properties. It's experimentally relevant. It has connections to quantum annealing or quantum adiabatic computers, and it also has connections to condensed matter. I think lithium holmium fluoride was a quantum crystal that has a Hamiltonian very close to what we're going to talk about. I think it has some important deviations from transit field Ising model, but the transit field Ising model is this sort of simplest, I guess if you want to call it low energy effective model for lithium holmium fluoride. Okay. And it also illustrates the classical and quantum stat-mech link. So we'll develop that link sort of by example first, and then we'll do it a little more abstractly in general. So let me set all my important constants equal to 1. So Planck and Boltzmann constants. Okay. Hope this doesn't perturb the experimentalist. We can insert those later if we ever need to, and you can sort of just throw them out and then put them back in with dimensional analysis if you ever need them later. And let's now define a lattice model. For spin 1/2 degrees of freedom. Okay, so place spin 1/2 operators, so quantum operators, on the vertices of a lattice. And there's many different lattices that you can choose.
Is it all 3D?
No, we'll talk about hypercubes. So we're going to do general dimensions. So that's important in the development of this type of theory, that you don't restrict yourself to a dimension. So for condensed matter applications, of course, you're only dealing with 1 dimension, 2 dimension, or 3 dimension. And so most of the time, you're talking about one of these 3 dimensions. But different dimensions give you different computational tools. So infinite dimensions gives you access to a very simple sort of mean field picture that you can solve analytically. But it doesn't mean anything, right? Infinite dimensions doesn't mean anything. Very low dimensions quite often can be solved exactly, but that's kind of a restricted case. Like a 1-dimensional, say, electron fluid or something like that, it's actually very rare in nature. So the lattice will be kept in general dimensions as much as we can. And to start, I'm going to talk about hypercubes. The role of the lattice is very important in condensed matter field theory because you leave the lattice in the theory. So why do you do that? Well, number one, you might be dealing with a condensed matter system that is a crystal that has a specific lattice essentially given to you by nature. And that's not necessarily a hypercube. There's all sorts of interesting lattices out there. Pyrochlores are very common in 3 dimensions, corner-sharing tetrahedra. 2 dimensions, things like triangular and Kagame lattices are very interesting and common. So, you know, there's lots of different lattices that can occur, and if you're going to do condensed matter field theory, the symmetry of that lattice has to go into your effective theory. There's another perspective on lattices. It's that if you start with a continuum theory, which is if you do a high energy course, if you take this course with a high energy theorist, you'll start with a continuum theory. You'll have quantum fields in the continuum. and you'll regularize those onto a lattice. You'll essentially discretize space as sort of a computational trick. And then you typically end up with hypercubes. So I'm just kind of meeting in the middle here. I'm just going to start by imagining that I have a hypercubic lattice that, you know, we could extend to other types of lattices if we need to. So on some of the assignments and some of the, you know, in the computational project, we'll actually look at different lattices. That's a D equals one-dimensional hypercube. I guess it's the same, you know, for anything, not even a cube. There's only one type of one-dimensional lattice. D equals 2 is square. D equals 3 is cubic. You know, it's like the spin 1/2 degrees of freedom sit on the vertices, right? So if I wanted to make a cubic lattice, I can imagine making a degree of freedom on the vertex, and then 3 edges of the graph. And these edges we'll call bonds because they're related to you know, an actual energetic bond in the model. And I can imagine just displacing this x, y, and z. So I move it 1 over. You know, it looks like this in the x direction. If I move it 1 over in the y direction or the z direction, I can move it over. Okay, that's ugly, but you get the idea. And then you can have 4-dimensional, 5-dimensional hypercubes, and so on. So we'll just leave this dimension general to start with. We'll label the number of lattice sites. Is n. So here's n equals 1, 2, 3, 4, 5. Here's n equals 9. And that's the same n as I'm talking about here. Right, so the dimension of the Hilbert space depends on that n. And then boundary conditions. Which is how, say in one dimension, how is this site related to this site? That's what the boundary condition means. These can be periodic or open. Okay, and it matters. You get different energies. You get different, you know, properties of the system depending on whether or not you're periodic or open. In the end, it shouldn't matter if I extrapolate to the thermodynamic limit. Okay, so this would be open. Periodic would mean I have a bond that connects like this. Or I could have drawn that whole thing as a ring, just a perfect circle. That's another way of showing periodic boundary conditions. So typically you choose boundary conditions based on what's convenient, you know, in a computational sense. And then you try to make the system bigger and bigger. You try to take some length scale and scale it to infinity so that in the thermodynamic limit, you know, the boundary condition doesn't matter. So we'll just use whatever works best for us. So let's label each site with an I. Okay, so our spin operators. I'm not going to draw the hats or the arrows or whatever. Okay? They're just given in terms of Pauli matrices. So if I drew this as a, yeah, okay, so I drew it as an operator here. So the Pauli matrices can be written in terms of x, y, or z, of course. One, zero, zero, minus one. Okay, so the Pauli matrices are what sit essentially on the vertices of the lattice. They're your qubits. If you're constructing a superconducting quantum circuit, that circuit is a bunch of qubits connected with these edges, if you want to call it that, right? So you probably know the commutation relations for spins. The important thing to note in a many-body system is operators on different site labels commute. So I can write the commutation relations as B, J. So I got I and J. A and B are my component, X, Y, or Z. This is that Levi-Civita symbol, S, C. And I put a delta function for site ij. Okay, so that's just -1. If it's x, y, z, it's 1. If you permute any of those indices, you get a minus sign in this symbol. Right, and A, B, C equals x, y, z. Sometimes I'll write that as 1, 2, 3.
Why is there a vector 2 again in your spin representation? Your spin operator?
Why?
Yeah.
Just definition. It's just when you develop the theory of angular momentum. So if you do it in 334 or whatever it is, then that factor of 1/2 is sort of natural. So spin 1/2, is the it's the most fundamental sort of representation of the angular momentum operator in that sense. And so it comes out physically when you're dealing with angular momentum. But we're not really explicitly talking about angular momentum here, so we don't necessarily use it. And if you can write Hamiltonians in terms of either or, and it's just that factor. So it's just when you deal with spin 1/2 Hamiltonians, sometimes they're written in terms of spins, and sometimes they're written in terms of Pauli operators. And all you got to do is remember that factor of 1/2. So I think it's just convention, whatever people are most used to. I think for transverse field Ising models, people often write them in terms of Pauli operators, and that's what I'm going to do. But if you're dealing with Heisenberg models or XY models or something like that, often those will be written in terms of the spin, the S operator. So just be used to going back and forth and not forgetting that factor of 2. So the basis, or the basis state, will be made up of the eigenstates of sigma z. Okay, so we've chosen, just as you choose a preferred axis for the angular momentum operator when you're deriving these matrices, we'll just choose sigma z as the basis, but you don't really have to. It's an arbitrary choice. It's just convention again, right? So you can represent. So if I have a sigma z as a basis state, let me just write that as without the z. So I'm just going to write it as sigma. Okay, so if I apply, this is what defines this. So if I apply the operator, so this is the only thing that gets confusing if I leave out the hats, right? So if I apply the operator to that basis state, all right, then I retrieve sigma I as the eigenvalue. Okay, this is common in textbooks too. The other option is you can call this S or something like that, small s. But I don't like using S because it confuses this factor of 1/2. So let's just stick with the sigmas. Sigma I can be this eigenvalue, right? Can be plus or minus 1, or plus or minus 1/2 if you're dealing with spin 1/2. And you can also call that arrow up or arrow down, say. So then for some site, some isolated site. The eigenequation for this operator is just this. And this is an orthonormal basis, right? So if I have on one site, right, a prime and an unprimed basis state, you only get unity if they're the same state. Okay, and if they're on different sites, if the I label is different, again, things commute because you have that delta ij up there. Okay, so that's the sort of single site properties. For the many-body system, we define the Hilbert space with a tensor product. So for the transverse field Ising model, and I'll use the notation. Okay, so this is for a single site I. So I'll use the notation, I guess, the set of all sites I, which really just means tensor product all the way up to sigma big N. Okay, and this could also, as an example, a basis state of n spins could be up, down, up, down, whatever, right? So again, we're going slow. It seems complicated, but really all I'm talking about is all the sigma z spin up or spin downs as the basis. If there's n sites, so if there's 0, 1, 2, 3, 4, I started with 0. I'm used to C++. So 1, 2, 3, all the way up to n. If I label those sites, right? So it could be, it's this label, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then this is where your 2 to the n Hilbert space comes from. Because each one of these sites can either have a spin up or a spin down. So that's your 2 to the n Hilbert, it's the size of your Hilbert space. Right? Makes sense? And the matrix element for, okay, well, so the orthonormal condition which follows straightforwardly. I'm just writing this stuff very explicitly here. So let me say sigma I prime, sigma I unprime. This is now just the product of these deltas, right? So it's a product from I equals 1 to n. Let's see. Delta sigma prime I, comma sigma I. I buy it. We'll calculate the matrix elements quite often for single operators. So the matrix element for a single operator So a single operator meaning a single site, say, on this lattice, is just let's call it, what am I calling these things? I see my notation. If I want to avoid the hats, whatever, I'm just going to write them as an S. Who cares? That's my operator. And A, B, or C. Oh, I could write a sigma A, B, or C. So this is just the product of all. This is I've labeled this specific site J. So this is just the product of all I not equal to J. Sigma I, sigma I. Then specifically for J, so whatever that S is, okay, so when I'm a many-body state, and I want to calculate the expectation value of an operator, right? So if it's like, I have to, and I'm only applying the operator to one site, J, I only get a non-zero expectation value if all these sites that aren't J are in the same state because it's orthonormal. And in addition, I don't basically change the state with that S operator, right? So if there's no prime here, if these two states are the same on the left hand and the right hand side, if the bra and the ket are the same state, say, I don't know, up, 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 make them all ups, right? Then the only operator that would give me a non-zero expectation value would be something diagonal, like sigma z I, or j, sorry. Say this is site j here, right? So this would give me a non-zero expectation value. If this one started down, then only sigma x, or say sigma x, would give you a non-zero expectation value because it's going to flip that spin. And say this site was down here, and it's not the index of the operator, then the expectation value will always be 0, right? So that's just how, because of this commutation relation, because of the sigma ij here, that's basically how everything works. Okay, so that's how you deal with operators. And then what remains is this thing here, right? That's just a 2x2 matrix, right? So let me write the Hamiltonian for the transverse field Ising model. So call it H. Put a minus sign. Thus called because this is an Ising model. Okay, so Jij is called the exchange, or the exchange constant. Because it operates between two different spins. And H is called the transverse field. And it's transverse because the Ising term has sigma z's, and the field term has a sigma x. If everything was sigma z, say, or sigma z, depending on what country you're in, then this would just be a classical model, classical Ising model. But that transverse field is what gives you something interesting. So, as an example, I mentioned quantum annealing algorithms in quantum computing. This transverse field Ising Hamiltonian is exactly the Hamiltonian that is purported to exist in D-wave, where these exchange constants are just connected in some complicated graph. So what happens in D-wave is instead of having a hypercubic lattice, which is what I want to deal with, you have something they call a chimera graph. So it's a transverse field Ising model with a chimera graph instead of so all the theory behind D-wave is essentially this Hamiltonian with complicated graph that I won't even draw. It basically has blocks of something like 8 qubits that are connected in a certain way within the blocks, and then each one of these qubit blocks is transposed, and there's connections between the blocks. So this chimera graph is something to do with, it's defined because of restrictions on their hardware. What I want to do to start out is simplify the exchange constants, which right now can occur between any I and j. All right? So I can have an exchange between, so this is 1, 2, 3, 4, 5. I could define a transverse field Ising model that has a jij between 1 and 3, if I wanted to. 1 and 3. Or between 2 and 5. I have no restrictions on that exchange constant right now. But let me impose a restriction. And that restriction I'm going to impose is that I'm just going to call this thing J if I and J are nearest neighbors. In the hypercubic sense. Nearest neighbors meaning, nearest neighbors are defined by these lines. Okay? So that's why we drew these lines and I called them bonds. So these are bonds. And then it's 0 otherwise. And then what that means is the Hamiltonian is often written as minus sum over angle brackets ij, which means nearest neighbor. You can put the j on the outside then, just this constant j, sigma z I sigma z j minus h I sigma x I. Okay, so picture that thing where each one of these is your j, and then there's an overall transverse field that's applied in the x direction. Who's seen this Hamiltonian before? 4 or 5 of you. Okay, all right. So that's as slow as we're going to go in this class. From now on, we're going to start picking things up a little bit. We're going to take this transverse field Ising model, and we're going to do a quick perturbation theory, sort of a physical way of determining the broad features of the phase diagram tomorrow, or Thursday. So once we get the broad idea of the phase diagram, the different phases, then we're going to essentially derive explicitly the quantum to classical correspondence of this thing in d+1 dimensions, little d+1 dimensions. Okay, so I'll see you guys on Thursday.